Today, we're going to take a look at an approximation algorithm for the set cover problem. So what is a set cover problem? What is a set cover? We have a set of elements. We call this set U. So that's a universe or ground set. And we will depict the elements as these blue dots. Now we have a family of subsets. So for instance, we have the set here S1, 2, and up to S6. So this is now our family of subsets. And they should jointly cover all of the points. And we're now interested in a cover, which is a selection of these subsets, which cover all points. Or taking all of these subsets, for instance, would be a cover. But we want to have the minimum cardinality cover. So we want to select as few sets as possible, such that all points are covered. So in this example, what would be a minimum cardinality cover? How many sets do I need to select to cover all points? So here 4 sets are enough. These sets S1, 2, S4, and S6. Now, the generalization of this is a min cost or min weight cover. How does that look like? Now, each of the sets has a cost. And we do not want to minimize the cardinality, so we do not want to minimize the number of sets, but we want to minimize the total cost, which is the sum of the costs of the sets that I selected. So in this example, we could have these costs. The one set costs 3, 1, 4, 4, and so on. So now again, the question is, what is a min cost cover in this thing? So is this cover already min cost? This one isn't. This would be the min cost cover here, because taking out the set with cost 6 and instead of replacing it by a set of cost 1 and 4 reduces the cost by 1, and still all points are covered. How can we see that this is an optimal cover in this example? So that is quite simple. So there are certain points that are only covered by one set. So this point, for instance, is only covered by that set. So we'll have to select that set. Likewise, this point and that set, this point and that set. So essentially, the only question is, how do we cover those 2 points? And there we have the choice between taking the set that has cost 6, which in the min cardinality setting would have been the best choice because it just adds 1 set. And in the min cost setting, the 1 plus 4, so 5, is smaller. So that's a set cover and the set cover problem. And now we're going to see an approximation algorithm, and that will be a greedy algorithm. And for that greedy algorithm, we first have to think about what is a good greedy choice. So for that, let's think about what does it cost to select an element or select a set and thereby also getting elements covered, or this buying elements. Now, if you look at this set here, it has a cost of 4. It also covers 4 points. This would have a cost of 4. It only covers 3 points. So it's important what is the cost of the set, but also how many elements do I cover. And therefore, we look at the per element cost. Per element cost set is the cost of the set divided by the number of elements that I gain. So here, for this set, that would be 4 divided by 3. For the larger set down there, with 4 elements and cost 4, that would be 1. And so on. So one set with cost 1, I get 1/3. And in that way, I can, for each set, compute the per element cost. Now, if I would select such a set, so if I, for instance, select the green set here, then I would have to do the following. First of all, by selecting that set, I get those elements and I assign this 4/3 as price to those elements. And also I will need to recompute the per element costs for some of these sets, because some sets, now certain elements are covered, which previously weren't covered. So then I have to for instance, for the set up here, where I only have 2 elements left, now the per element cost goes up to 1/2. Or for the set down here, now only 3 elements are left, so now I have a per element cost of 4/3. And if I now would select it, I would buy these remaining elements for a cost of 4/3 and update the cost, the per element cost for the other sets accordingly. And we could continue. Eventually, we can also be in a setting here, for instance, where the set, so all elements in that set are already covered. So then I would never select that set anymore. So I set per element cost to infinity. Let's say now I buy that last set there, and then I can calculate the total cost of the cover. And this is now simply the sum of prices that I paid for the elements. I can add up all of these numbers here, and this gives me then the cost of this cover. And the natural greedy choice now is always take the set with a minimum per element cost. So before we look at pseudocode for this, what does that mean for the setting where all costs are 1? So where every set costs 1, or differently, where we're back to the min cardinality setting. So what is the greedy choice there? So since all costs are 1, or every set costs 1, we get 1 divided by number of remaining elements. So we're always going to pick the set with the largest number of remaining elements. Now let's look at pseudocode for the algorithm. So we will have the set of covered elements. See, initially that is empty. The set of sets that we selected, which also initially is empty. So as long as there are still elements to be covered, as long as the covered elements is not yet our universe, we do the following. For each set, we need to calculate the per element costs. We have those here, cost of the set divided by number of remaining elements. That would give me these numbers here. And then I take the smallest, the set with the smallest number. Here the smallest number is 1/3. That would be my set S, which I want to select. What I do is for each element in that set that hadn't been covered previously, we set the price to the current per element cost here. Then we're going to add those elements to the set of covered elements. Do that by taking a set of covered elements, the previously covered elements union with our current set, and we add our set to the set of sets selected. So here we now have already the per element costs for the remaining sets updated. What would be the next step? Next step would be we take again the one with the minimum per element cost, is this one, 5/6. Then for each of these elements that are remaining, which are 3, we would set the price to 5 divided by 6. We would add those elements to the set of covered elements, and we would add that set to our set cover. Now let's analyze this algorithm. We get the following approximation factor. If k is the size of the largest set in our set of sets, then the approximation factor is the kth harmonic number, which is defined as 1 plus 1/2 plus 1/3 up to 1 divided by k, which is roughly the natural logarithm of k. Or if you want to have a bound in n, then the cardinality of the largest set is obviously bounded by the number of elements n. So then we would get a bound in log n. To prove the theorem, we need the following lemma. And you should think of this set S in the lemma as an arbitrary set. So not one that the algorithm selects. Actually, we will use this lemma for the sets in the optimal cover. So this is an arbitrary set of the set of sets. It has L elements, U1 to UL, which we have now sorted in the order in which the algorithm, so the greedy algorithm, picks those elements. And of course, some of these might be picked at the same time, then it doesn't matter how we order them. But we can now argue that the price of the jth element is bounded by cost of the set S divided by this number, L minus J plus 1. So the proof is simple and as follows. We look at our algorithm, so we have this while loop, and we look at the iteration where uj is covered, so where we buy uj. So at this point, at most j minus 1 elements from this S, the set S, have been previously bought. Why is that the case? Because we have said uj is a jth element that is bought. So the only thing that could happen is that some other elements that come previously later are bought in the same iteration, but then the number of previously bought elements just goes down. So we have at most j minus 1 previously bought elements. That means that since we had L elements overall in the set S, that at least L and then minus this number, j minus 1, L minus j minus 1, which I can rewrite as L minus j plus 1, at least that many elements of S remain at this point in time. Yeah, so we have at least L minus j plus 1 elements remaining, elements that haven't been bought yet. This means for the per element cost of S in this iteration, that its cost would have been, or the per element cost would have been cost of S divided by number of remaining elements, and since this is at least L minus j plus 1, the per element cost is at most cost of S divided by L minus j plus 1. Now the greedy algorithm always picks the set with the smallest per element cost, meaning that the per element cost of the set that we actually chose, which could have been S, but which also could have been another one, is at most this number. And being at most this number means that the price, so that is a price that I assigned to uj through the greedy algorithm, is at most this number. So we've proven this lemma. From this lemma, we easily get the following corollary. If we define the price of a set in a set of sets as the sum of prices of the elements in that set, then we can bound this by cost of the set times L's harmonic number, assuming that L is the size of the set S. And this follows immediately from the lemma. So let me just write this sum again. We have the sum I goes from 1 to L. The price of ui I can bound by this here with I here. So this is T, the cost of S, divided by L minus I plus 1. So let's take the cost out of the sum. So write it here. And then I have the sum 1 divided by, and let's just think about if you plug in L, you get L minus L plus 1, so 1 divided by 1. And this then goes up. If I do L minus 1, then it's L minus 1 plus 1. That's 1 divided by 2. And this goes down to when I is 1, I have L minus 1 plus 1. So simply L. So I have 1 divided by 1, 1 divided by 2, up to 1 divided by L. This is exactly the definition of the Lth harmonic number. So this corollary follows. With this corollary, we can now prove our theorem. For this, we look at an optimal solution. So a solution that gives us a minimum cost set cover. Let's call those sets in that solution S1 to Sm. So then the objective function, the cost of the cover, is simply the sum of the costs of those sets. Now let's compare that to the cost of the greedy set cover. We can write the cost of the greedy set cover as the price of u. Price of u, what I mean by that is simply sum of the prices, all elements in u. Because price was the number that we assigned in the algorithm as a per element cost of that element when we bought it. and then the sum of that exactly gives us the overall cost of that. Now, each of these elements obviously occurs in at least one of these sets here, because it's a set cover. Each element occurs in at least one of those sets. So I can bound the sum of the prices of the elements by the sum of the prices of these sets, because each number here occurs in one of those sums here, at least one of those sums. Element which is covered several times also occurs in the sum several times, therefore I just get a smaller equal and upper bound. But now I can apply the corollary, so I can replace this price by the cost of S times the Lth harmonic number. I can additionally, if K is the largest cardinality that occurs, I can bound HL by HK. Therefore, this sum I can bound by sum of the costs times the K's harmonic number. Now the sum of the costs, that is exactly our opt. So we have now opt times HK, meaning we have an approximation factor of HK. Now we have HK as an approximation factor. The question is the analysis tight? Is this actually the approximation factor that the algorithm achieves, or does it achieve a better approximation factor? So we can prove that this is actually the best that we can get, and we do this using an example, and that is the following. So now we have lots of one-element sets and one set that contains all elements. Now let's assign suitable costs. So for the large set, we have a cost of 1 plus epsilon. For the small sets, we have costs 1 divided by n, 1 divided by n minus 1, 1 divided by n minus 2, and so on. So now let's think about which sets does the greedy algorithm select. Therefore, what is the cost of the set cover that we compute by the greedy algorithm? And in contrast, what is the cost of the optimal cover? The greedy algorithm looks at the per element cost. For those green sets, the smallest one is 1 divided by n. So the only other choice we would have is the red one, but there we have 1 plus epsilon divided by n, which is slightly larger. Therefore, the greedy algorithm will first select this set. Then essentially it has a choice between 1 divided by n minus 1 versus 1 plus epsilon divided by the number of remaining elements now is n minus 1 too. So again, this is slightly larger, so we're going to select that one, and so on. And at the end of the day, the greedy algorithm simply selects all of those green sets. Now let's sum up those weights. 1 divided by n, 1 divided by n minus 1, up to 1. This is exactly the definition of the nth harmonic number. So the algorithm computes the solution which has cost h of n, while the optimum would have been simply select the red set, and then we would have had 1 plus epsilon. If you look at the quotient, then this is close to h of n, and epsilon as small as we want to. So the algorithm indeed has this approximation factor. We can now, of course, ask, maybe there's a different algorithm with a better approximation. Can we do better? Unfortunately, no. So it is known that unless p equals np, there's no polynomial time algorithm that approximates set cover within a factor better than omega of log n, or making this tighter statement here, 1 minus small o of 1 natural logarithm of n. Yeah, so the greedy algorithm is already as good as it gets. Before we wrap up, let's look at one interesting special case, and that is vertex cover. The vertex cover can be seen as a set cover problem. Maybe pause for a moment to think about why that is. In vertex cover, we want to cover the edges. So our universe is a set of edges. And now we cover the edges by selecting vertices, and when I select a vertex, it covers the incident edges. So the sets that we have for every vertex vi, I have a set Si, and I exactly get the edges where vi is incident, where vi is one of the endpoints. As an example, if this is our graph here, then I have lots of one element subsets here because each of these outer vertices only covers one edge. And then also for this vertex here, that vertex covers all edges, so I also have this big red edge, a red set here. So in this setting, what does the greedy criterion say? Which vertex do we choose? Let's take a look. So here's again a graph. We have all of these edges that we want to cover. Every vertex covers a certain set of edges, namely the ones incident. So for instance, if you look at the vertex V8, it covers E7, E8, E9, E10, E11. So this is this set here. And the per element cost, so we're doing min cardinality vertex cover here. So every set costs 1, but the per element costs then 1 divided by number of remaining elements. That is the remaining degree of the vertex. So I always take the vertex with the largest degree, where I assume that edges that I've already covered, I delete. So here, for instance, I would first select this one because it has the highest degree, and then continue. To wrap up, let's take a look at the approximation factor once more. We had this approximation factor of hk, where this is a kth harmonic number, and since k is smaller or equal to n, we have a bound of O of log n, and this is as good as it gets.